In this problem, we want to determine the magnitude and the direction of the resultant force that acts on the bracket due to the tension in the three ropes. In the tension in the three ropes, this rope acts straight upward, this one acts to the upper left, and that one acts to the lower left. And what I mean by resultant force is if we could effectively remove the three ropes and make a hypothetical rope that would result in the same force acting on the bracket. In this particular problem, we've got the force, we'll call this F1. There's a force of tension of 30 pounds acting straight upward on the bracket from that rope. F2 is equal to 75 pounds acting to the upper left. And F3 is equal to 10 pounds, which acts to the lower left. And in essence of what we want to do, let's get rid of all three of these ropes. And in essence, again, what we want to do is figure out in what direction would we have to place a single rope, and how hard would we have to pull on this rope to result in an equivalent stress or an equivalent force acting on the bracket. The resultant force will be the vector sum of all three of these forces, and it might be a little bit easier to see what we'll come up with as if instead of drawing the same length arrows for all three of these, I'll draw them more or less to scale. So here I've drawn the force F2, 75 pounds, much longer, about twice as long as F1, and a great deal longer than F3, which is only 10 pounds. So if we looked at this, think about doing the vector sum of these quantities. If F2 is really large, let's say, I don't know, 1,000 pounds, then the resultant force will essentially fall right along F2 because F1 and F3 are just inconsequential in that case. However, in this case, it looks like F2 being a little bit longer. I would expect a resultant force, maybe something like this, being pulled upward by F1, a little bit downward by F3, but it'll point to the left, and in general, it'll be fairly close to F2. And what we want to figure out is the magnitude of this hypothetical blue arrow, the resultant force, and we also want to figure out the angle from the horizontal. And to do that, we'll need a little bit more information. We know that F1 points straight up. In F2, for this problem, it is at an angle of 60 degrees from the vertical. And F3, what we know is the slope of F3. And I'll indicate the slope of F3, and it's got a vertical, it's got a vertical rise of, let's say, 3 inches or 3 millimeters or whatever unit for every 4 that you move along in the horizontal. So this, if we examine this, it's convenient in this case because this is the 3, 4, 5 right triangle, and we can use that to establish the angle for F3. So let's establish our coordinate axes. I'll use the convention I hat for the horizontal and j hat for the vertical. And the resultant force is going to be the vector sum of F1 plus F2 plus F3. We need to write each one of these in vector form. So F1, it's acting only in the vertical direction, so that's going to equal 0 pounds in the I hat direction. There's no horizontal component, plus 30 pounds in the vertical direction, or the j hat direction. For F2, we'll have to do a little bit of trigonometry. It acts to the left, so in the negative direction, negative 75 pounds, we do a little bit of trig times the sine of 60 degrees in the I hat direction. And in the vertical direction, we have 75 pounds times the cosine of 60 degrees. For F3, there's a couple of different ways that we could write this in vector form. First off, we know that it acts to the left. There's negative 10 pounds acting to the left. And if I look at this, the left component would be 4 divided by 5 will give us the fraction of the force acting in the horizontal or to the left. And it also acts in the downward direction, 10 pounds times 3 over 5 in the j hat direction. To demonstrate how we can do this, I've taken the rope 3, and I'll zoom in on it. Again, we've got this 3, 4, 5 triangle, and I'll define some angle, we'll just call it gamma. By trigonometry, we know that the sine of gamma is equal to 3 over 5, and the cosine of gamma is equal to 4 over 5, and in both cases I'll come up with a value of gamma of 36.87 degrees. So let's write F3 in terms of gamma. Again, we've got negative 10 pounds, and in this case it'll be multiplied by the cosine of gamma in the I hat direction, and also it'll act downward, magnitude of 10 pounds times the sine of gamma in the j hat direction. But by trigonometry, we've already established that the cosine of gamma is equal to 4 over 5, and the sine of gamma is equal to 3 over 5, so you'll see both expressions are equivalent. I just find it easier to write 4 over 5 and 3 over 5 to begin with if I already know the slope for the problem. Let's just stick with the first notation since it's a little bit easier. And I'm going to compute the vector sum. I've got 0 pounds in the i-hat direction, this value in the i-hat direction for F2, and this value in the i-hat direction for F3. So if I write out the resultant force, I'll just compute the sum of all three of those. So here I've computed the sum of the three in the i-hat direction, and I'll compute the three in the j-hat direction. So here's my vector, my resultant force. And when I simplify that, here's my resultant force. Negative 73 pounds acting to the left and 61.5 pounds acting in the vertical direction. And that's enough to answer the problem, but we can also, let's just determine the magnitude and the direction of this resultant force. Here's my resultant force along with a right triangle to describe it. We've got 73 pounds acting to the left and 61.5 pounds acting in the vertical direction. We want to figure out this value, theta. With a little bit of trig, we find that theta is equal to the arctangent of 61.5 pounds divided by 73 pounds. And that's equal to the value of theta of about 40 degrees. So this means that the resultant force, if we replaced all three of these ropes and we applied a rope, it would act 40 degrees upward from the horizontal, and that would apply the exact same loading on the bracket. We also need to figure out how much tension we would need in our hypothetical rope. So we'll just say Fr here without the vector form is just equal to the magnitude of the resultant force, and that's equal to negative 73 pounds squared plus 61.5 pounds squared. And we'll take the square root of that, just Pythagorean theorem, and we come up with a magnitude of 95 pounds. We've got a 95-pound rope acting 40 degrees above the horizontal to the upper left, and we'll come up with something exactly equivalent to the loading of these three ropes. And what's useful to note is at the beginning we examined this, and I took a stab. I guessed that the resultant force would be something like that, driven upward a little bit by F1 and driven primarily by the large tension in F2. And if we look at this, I know that by our vector sum we have an angle of 40 degrees. So this angle here for F2 is equal to 30 degrees above the horizontal. We find that the resultant force here resulting from the three ropes is indeed a little bit larger than 30 degrees, acting a little bit more to the upper left than F2. So again, if we took a single rope and we applied it 40 degrees upward from the horizontal, and we applied a tension of 95 pounds to that single rope, the bracket in this region would feel the exact same stress as it would as if there were three ropes in the original configuration.